Welcome, everybody. Thanks so much for joining me today. My name is Brandon Minnick, and in this session, we're talking about correcting common async await mistakes in .NET. Now, we've got a ton of material to cover. Async await is crazy complex, which is probably why you're all already here. So we're going to move fast, and there's going to be a lot of stuff we're cramming into this session today. So we'll save all the questions for the end so that we can get through everything in the hour. But the good news is, don't worry about taking any notes. Don't worry about having to keep up if you miss anything. Because if you head to my website, you can scan this QR code, takes you to codetraveler.io/async await best practices, and there you can find everything we're covering today. That's where you can find a recording of this talk, so if you miss anything, you can always go back and see it again. It's where you can find the slides. It's where you can find the open source sample that we're going to be building together. It's where you can find some NuGet packages I recommend, and also courses if you want to learn even more on async await in C#. And if we don't get around to answering any of your questions today, you can find me online. My Blue Sky handle is down here, codetraveler.io. You can find me on all the socials as the Code Traveler. My messages are always open, so feel free to shoot me a message if you have any questions, if you have any follow-ups. But let's get into it. So let's start by looking at this method called getLibraries. This is a public async task method. It returns a task of type list, of type library model, and probably something we've all done before, right? We're making a get API call, deserializing it, and returning that result. So what we're doing is we're calling HTTP client.getAsync, hitting an API on my website. Then we're going to make sure that we ensure it's a successful status code. If it is, great. We'll read the stream, we'll deserialize it, and we'll return the result, assuming it's not null. But what's really going on here under the hood with multi-threading and async await? Well, let's assume that thread 1 calls this method. So thread 1 enters getLibraries, and it initializes this variable response, and then it immediately hits this await keyword. And when a thread hits the await keyword, that thread returns, and now getAsync here is running on a background thread. In this case, we'll say thread 2. But this can be any background thread. The way .NET works, it has something called a thread pool, which you can think of it like a bucket of threads. And .NET, when you run your app, will look at how powerful your machine is and determine how many threads it can allocate. So if you have a super powerful server up in the cloud, then you'll have a ton of threads. If you have a really weak laptop, you'll have fewer threads. But you don't have to worry about that. .NET does it for us. So here, .NET went to the thread pool, said, hey, what thread's available to run getAsync? Thread 2 said, I'm available. So thread 2 is now running this on the background. And like we said, thread 1 returned. So thread 1 is now free. And this is really, really important in .NET because thread 1 is also known as the main thread. It's also known as the UI thread. And it's the only thread that can draw the UI. So when you launch a desktop app, mobile app, it's thread 1 that's painting everything to the screen. And thread 1 is also the only thread that can interact with the user. So when a user's scrolling your app, when a user's tapping buttons, it's thread 1 that handles that button click. So thread 1's super, super important. And so thankfully, with async await, we're able to free up thread 1 and not have thread 1 running getAsync. Because let's think about if thread 1 was running getAsync. Thread 1's making an API call now. If this API call takes 5 seconds, well, to the user, our app would essentially be frozen for 5 seconds. It would mean that while thread 1's busy, the user can't interact with the app. They can't scroll, they can't tap. And for me, I'm a mobile app developer. I've been making mobile apps in C# for over a decade now with Xamarin and .NET MAUI. So what happens to my apps is the user goes, this app froze, because they're not going to wait 5 seconds. They force quit the app, give me a 1-star review in the App Store, and tell everybody my app sucks. But thankfully, we have async await. So thread 1 is free to interact with the user. Meanwhile, a background thread, in this case thread 2, is running getAsync. Now, when thread 2 is done, this task implements something called a waiter, which implements an interface called iNotifyCompletion. And that completion is what shouts out to .NET to say, hey, I'm a task and I'm completed. So once thread 2 finishes getAsync, it goes, hey, .NET, I'm all done. .NET goes, great. Who called you? Who is your calling thread? And in this case, thread 1 was the calling thread. So .NET says, hey, thread 1, get back in here. And thread 1 jumps back into the method, picking up where it left off. And now thread 1 ensures that we have a successful status code and initializes a stream. But just like last time, thread 1 hits this await keyword and returns. And now read a stream async is running on a background thread. We'll say thread 5. But again, this is whatever thread is available and free in the thread pool. And so read a stream async completes, notifies .NET. .NET says what thread called you, what was your calling thread. It says thread 1. .NET says, all right, thread 1, get back in here. Jumps back in to initialize the variable libraries. But again, hits an await keyword, returns, is now again free to interact with the user, scrolling, swiping, whatever the user's doing while we deserialize this object in a background thread. It finishes, thread 1 jumps back in, and will return the result of libraries, assuming it's not null. So what's really happening here? Well, to understand, we got to go just a layer deeper, because you might not know that .NET takes our code, or rather the .NET compiler, takes our code and generates all this code we see here on the right. Look at all this code. We didn't write this code. This is the code we wrote on the left. And if you've never heard of this website, by the way, awesome website, sharplab.io. You can use it to type in your C# code, and you can see what the compiler generates. You know, if you want to look at the assembly level code, you can dig all the way deep down there. Kind of like reading the matrix if you're not familiar with it. But what we're looking at is the compiler-generated code kind of uplifted back to us in C#, so us humans have an easier time reading it. Now, what we want to look at here, and what we're going to dive really deep into, is the compiler has generated this thing called an async state machine. But what I want to show you first is, where's our method, right? There's still a method in here called getLibraries, but we've got to scroll all the way down. Keep scrolling. There it is. And here is our method signature. So public task list library model get libraries, public task list library models get libraries. But none of this code is my code. I didn't write any of this code. This is all compiler generated. Now, if this is your first time seeing this, don't worry too much. But at a high level, what's going on here is .NET is creating something called an async task method builder that's going to return this list of library models. And so we have some initialization steps here. And the important takeaway is it's building a state machine, and it initializes the state machine to be -1. So our initial state that we're going to enter into our state machine, -1. And then the builder kicks off this state machine. And what's funny now is this method is actually returning the task from this async task method builder. So whenever our state machine's done running, which we'll see in a second, that's when we return from this method. So again, it's our method signature, but totally different code inside it. And that's because our code lives up here inside of this async state machine. Now, the async state machine, again, compiler generated. The compiler creates a struct. It does that for some performance improvements. And cool little fun fact, we're looking at the release configuration. If you were building this in a debug configuration, you would actually see that it's a private sealed class instead of a struct. And if you kind of eyeball how many fields are here with the class in debug config versus the struct and release, you'll see that we get a bit of a performance optimization from the compiler. So now all that extra debug info there, that's for us. That's for us humans, when we set our breakpoints and we want to check variable results and what the values are. Like we still would need those variables in debug mode, but a couple years ago, .NET optimized the async state machine for us and was like, you know what? I don't think we need that much, and was able to shrink it down for us, which is great because that reduces our file size, or DLL size. So in this async state machine is a method called moveNext. Now, like I mentioned a minute ago, I've been making mobile apps for over a decade, always in C# with Xamarin and .NET MAUI. And when I first started getting into async await and started making my first apps 10 or so years ago, I'll never forget every time I got a crash report back. So if a user's using my app and it crashes, we have some telemetry data, sends me back the stack trace. And all these stack traces, I kept seeing moveNext. And I was like, what is this moveNext thing? Because I never wrote a method called moveNext. And it wasn't until I really literally dug into the compiler-generated code and was like, oh, the compiler is generating this code called moveNext for me. And so I was like, that's interesting. What does moveNext do? Well, if if you're already familiar with IEnumerable move next, you know move next is an iterator. So every time we loop through an IEnumerable, then we loop through move next. And it's kind of similar, but now this is an async state machine. So slightly different, but how's this work? So basically what happens is move next is a giant switch statement. So let's see if I can scroll down, scroll, all the way down here. Giant switch, and inside of this switch, we can start to see the code we wrote. Like here's http://client.getAsync. Here's things like deserialize async. So finally, like this is where our code lives. And one thing you'll notice, there's a lot of weird variable names. All these angle brackets, underscores. Kind of look past that. The compiler does that on purpose because the compiler doesn't want to generate code that would conflict with an existing class or method that I've written. So the compiler kind of cheats, which is fun, because if you try to create a struct, for example, called open angle brackets get libraries, you'll get a compiler error. That's illegal. We can't do that. But the compiler is allowed to break its own rules, and since it knows that it's illegal for me to generate a method or write a struct called angle bracket get libraries, then it knows if it does it, don't have to worry about conflict. So that's why you get these angle brackets, underscores, but if you squint a little bit, you can still see our code in here. So so we enter in this giant switch statement inside of move next, and we're switching on this local variable num, which is just initialized to that field state that we set earlier. And if you remember, we initialized this to be -1. And so I'm going to look in our switch for case -1, and I don't see it. We only have a default. We've got a case 0, we've got a case 1, a case 2. So that means we're going to start in the default case. And so we enter our default case where we call library service.getAsync. And what this is doing is it's grabbing the awaiter from that task, from getAsync, and assigning it to a local variable. And the awaiter, like I mentioned earlier, it's called a task awaiter in .NET. And it implements an interface called iNotifyCompletion, and it's this awaiter that fires its completion event to let .NET know, hey, I'm all done, you can come back and resume, and helps with the thread switching, which we'll see in a second. So actually, the first thing .NET does after it grabs the awaiter, so getAsync's running, this is off running on a background thread, and now we know the awaiter that's going to notify us, but it says, hey, before we do anything, is this task already completed? Because if the task is completed, then we don't need to switch threads. So in the example that we saw in the slides earlier, we assumed that every task was still working. It wasn't completed as soon as we called it. But if a task is already completed, we get this cool optimization from the .NET compiler that says, OK, cool, like you don't need to switch threads, and it'll just continue on down below in this switch statement. But in this case, we know getAsync's making an API call. It's going out to the internet. There's no way it could be completed right away. So it will never be completed in this instance. And so what do? Well, we set our state to be 0, and then we assign some fields, so like this u__1, this is a field up here. So we take our local variable from awaiter3, assign it to a field so that we can recapture that variable later. And then we tell that async task method builder what we're doing. We say, hey, we're awaiting the result of this awaiter. So in other words, we're waiting for getAsync to complete. And then we return. And this return statement is literally how thread 1 is able to return, exit our code, exit this method, and is now free to interact with the user. So it does, and awaiter3 or getAsync does its thing, and when it's done, this getAwaiter that's on every task will fire and let .NET know that it's complete. And again, .NET will always ask it, hey, what thread called you? And it'll, in this case, say thread 1. So .NET goes, all right, thread 1, you're back up. So thread 1 .NET tells thread 1 to come back into move next, and then we enter our switch statement again. But if you remember, we set our state to 0 before we left. So to pick up where we left off, we now switch on num, which is 0, which means we go straight to case 0. So get a little of initialization here, like we set our local variable from the field, and then we basically null out the field. We set it back to default. That's just a compiler or a memory optimization that the compiler does for us, so now it can garbage collect this field and not have to worry about it in memory. And then before we keep going, before we hit this goto statement to go to the next line of code, we set our state back to -1. And this is kind of weird, because -1 was the initial state, the default state. But now, like in the middle of our code, we're setting it again? Well, this is done on purpose, because what if the next line of code, like I call ensure status code, success status code, if that throws an exception because this HTTP response was not a 200, well, we're going to end this method. And so by setting state to -1 before we move on to the next line of code, it means the next time we call this method, the next time we call this task, that we'll start back at the top. Because if it didn't, and an exception got thrown halfway through our method, well then weird things would happen, like the next time we call the method, it would just pick up on the state where it left off. So don't worry about it. The engineers at .NET are really smart. They set it back to state equals -1 for us. And then we call this goto statement, which takes us down to IL_007E right here, where we get the result from awaiter 3. So we get our HTTP client.getAsync result. And then we're back into our code again. So we check the result to ensure it's a successful status code. Then we hit another await statement. So just like we saw last time, we get the read-to-stream asyncs awaiter, save that as a local variable, little optimization check to see, is it already completed? Because then we don't have to switch threads. And if it's not, then we update our state to be 1, so that when we jump back into the switch next time, when this awaiter is done, we'll jump to case 1. And same thing, we'll set our field, the value of this local variable, and then our async task method builder says, okay, now we're awaiting the result of awaiter 2, which we know is our read-to-stream async awaiter. So again, thread 1 returns when it's done. Thread 1 comes up back in, but now we go straight to case 1. And just like last time, a little bit of cleanup. We set our state to -1, and now we're going to this IL_00E7 tag, which is right here. And look at that, there's our code again. So deserialize async, but we're awaiting it. So what do? We get the awaiter. Yep, there it is, get awaiter. Set that value, check to see if it's completed. If it's not completed, let .NET know that's what we're awaiting, return. If it is completed, in this case, we're breaking. But if we returned and we jump back into case 2, would be right here, then similar cleanup, but now finally we hit a break, which means we can exit this switch. We've essentially reached our last await keyword. So something you might notice is here we use the await keyword 1, 2, 3 times. And so we have case 0, 1, 2. So we have 3 extra cases along with the default case because we're using the await keyword 3 times. So technically we have 4 because there's always going to be a default. So using the await keyword 3 times in our method, 4 cases in our state machine. If we were to use await keyword 5 times, we'd have 6 cases in our state machine. But now, what do? We hit the break, so we're exiting out of here. And just like you probably guessed, we get the result from, in this case, deserialize async. And we check to see if that's null, because if it is, we'll throw an exception. And if it's not, we do one more local variable assignment. Everything was successful, so we don't have to worry about this catch block here. We set the state to be -2. And then finally, if you remember, we were waiting on this state machine builder task. Well, finally, we can set the tasks, the builder's task result to be our list of libraries. That's it. Easy, right? Kind of crazy, but if you think about it, this is really, really cool because the code we get to write is this beautiful, elegant, human-readable code, whereas here on the right, gosh, if somebody submitted a pull request with this, I don't know what I'd do. Probably just be like, nope, try again. I can't read that. But what's great is the .NET engineers do this for us. But one problem that I see a lot, even with senior engineers, that they don't know that this switch statement exists. They don't know this compiler-generated code exists. And the big problem here is, look at this. Move next contains this giant try-catch block. Let's see if I can highlight it all here. There we go. So all of the code inside of move next, which is our code, is wrapped inside of this try-catch block. Now, I didn't write a try-catch block in my code, but .NET did for me. And what this means is if anywhere in my code, anywhere in my async task method, if an exception gets thrown, it's going to be caught here inside of move next, and that exception will be saved to the builder's task. Now, the good news is, as long as we await the task, .NET rethrows that exception for us. So the await keyword does a couple things. Not only does it allow the calling thread to return if the task is completed and push things on a background thread, not only will it get the result, but it will also look to see, was that task faulted? Was there an exception? And it'll rethrow it for us. And this is where a lot of .NET developers end up shooting themselves in the foot, myself included. Like, again, when I was first learning about this stuff, or first using async await without actually learning about it first, and I thought I knew how it worked, right? I was like, all right, task.run, that puts something on the background thread. I'm smart, I know my UI thread is thread 1, so I want to free that up. This is going to be running forever, doing database stuff. So task.run, do all this stuff on the background thread. Thread 1's free, great. And you know what? I don't care when this task.run finishes, so why would I await it? Like, it can run for 5 minutes for all I care. As long as it's on a background thread, I don't need to await it. But what I didn't know was by not awaiting the task, my exception was getting swallowed up inside of move next and never rethrown to me. And at first glance, it might be like, oh, that's a good thing, right? Like, exceptions suck. They crash my app. I hate them. Like, that's all my bug reports are because of the exceptions. But we know as senior C# developers that we want to gracefully handle exceptions. We should have a try-catch block that catches that HTTP response error exception. And we could do something like display a message to the user saying, hey, sorry, we couldn't get that HTTP result for you. Maybe check your internet connection, whatever it might be. We always want to await every task so that we get that exception bubbled back up to us. And it wasn't until I started experiencing weird bug reports with my app in the App Store where, like I said, I was calling task.run, making API calls on a background thread, and I was not awaiting it, bad. And so my code would just continue moving on like, hey, everything's still working. Nothing bad happened. Of course, that API call completed successfully. Why wouldn't it, right? And so you have this app get into like a weird state where like half the code thought it completed successfully, but it didn't. And so some buttons would work, some buttons wouldn't. The app would basically get in this unusable state. The user would have to force quit it, and yeah, that's how you get bad reviews. So this try-catch block, super, super important. I've never seen C# .NET really advertise this when they teach async await, but they really should, because again, if we don't await a task, we won't ever see that exception that gets thrown. Okay, so I know there's a lot to take in, so let's do a quick review. The async keyword adds about 80 bytes, and this is just because the compiler takes our async method and creates a state machine. So it generates that struct, and that increases our DLL size by 80 bytes. Now, this doesn't really matter. We're talking 80 bytes. We're not talking 80 megabytes. We're not talking 80 kilobytes. We're not talking 80 gigabytes, just 80 bytes. So this is more of a fun fact, unless you are one of the 0.001% of developers that, I don't know, maybe you're working on an embedded system and you really have to worry about the size of your DLLs. For the rest of us, fun fact, async keyword adds 80 bytes. Await every task, because non-awaited tasks hide our exceptions, and we want to handle those exceptions gracefully. When exceptions get swallowed up, our apps get into weird states where they're just broken, and as far as the user knows, it's garbage. Close it, don't ever use it again, restart it, 1-star review. Okay, so let's fix some code. I have an app here that, there we go. So .NET MAUI app that I built to go out to the Hacker News website. If you've never used Hacker News, it's a website where you can submit news articles, and then the other users will upvote, downvote, and kind of the most popular articles rise to the top. And it's all nerdy tech stuff. So like you can see the top story here is about Claude code. So I can click on the story, and if the internet connection, there we go. And then I can read the story here on my phone. So that's all we're doing. We're just getting the top stories from Hacker News so I can read them here on my device while I lay in bed in the morning without the will to get up and start my day. So what I have here is a view model. So in .NET MAUI, we always use the MVVM architecture. That means nothing to you. Don't worry about it. We're not talking about architecture design today. But I do want to mention, everything we're working on today is inside this class called bad async await practices. And when you check this out later, so again, don't worry about taking notes, memorizing anything. You can always open up the good async await practices class, and see all of the changes that we made and how this should have been written in the first place. So jumping in, we have our first refactor here at the top. And what's going on here? Well, if I scroll down a bit, I've got this method called refresh that I'm calling. And this is an async task method. It is the method that fires when the user does a pull to refresh. So this is what's going to refresh the list. So this goes out, gets the top stories from Hacker News, and then displays them into my top story collection, specifically sorted by the score of the story. And so back up here, we're in the constructor, but I want to run refresh as soon as this method launches, because it'd be a really poor app if the user just opened up a blank app and then had to manually refresh. Like, could you imagine, like, every time you launch Instagram, you had to first swipe? Like, that's not a good experience. So I want to refresh automatically for the user, at least the first time. And so I really want to call this refresh method here in the constructor, but I'm getting yelled at because, well, this is not awaited. And gosh, this error message, I wish they say, because here they say the current method continues before the call is completed. And that's true, and we'll talk about that in a second. But they never say anything about, hey, and also, if there's an exception thrown in your task, you're not awaiting it, you're never going to see it. I worked at Microsoft 7 years and tried to get them to update that warning message, and the best response I got was, why? Everybody already knows that. We don't need to put that in the warning message. It's like, okay. So right, we want to kick off this task in the constructor. So could we do something like this? Do async, await? Well, no, that just made it worse. That gives us more red squiggles because, again, we're in the constructor. You can't use async await in the constructor because constructors are just designed to allocate a section of memory, initialize an object, maybe we set a parameter or two, or a property or two, but that's it. Constructors are not long-running tasks. You'll never await a constructor. So we can't use the await keyword, but I just said we gotta await every task. So, well, one thing we could do, I could create another method down here called refresh. And then in here, I could pass in this method. And now I can await it, and then up in my constructor, I don't have to worry about getting those yellow squiggles anymore, and everything goes good, right? Well, yeah, I can see you're shaking your head, you're cringing, like, why? Well, it's because we just made an async void method. And what are we always taught when we first learn about async await? We're always taught async void's bad, don't use it. It's not bad advice, it's not wrong, but the problem I have with that is nobody tells you why it's bad. So why is this dangerous? Why is using async void here dangerous? Well, let's say I have some extra code down here where I'm going to do something more in the constructor to initialize my top story collection. Maybe I have some default data, or maybe I've got data stored in a database that I can show temporarily while I'm refreshing it. And so if we think about it, let's say thread 1 calls a constructor. So thread 1 enters the refresh method. Thread 1 gets here to the await keyword and returns. So thread 1 returns back up to here, but we are not awaiting refresh because we can't. If I put the await keyword here, red squiggles, you can't await a void. So thread 1 hits the await keyword, returns back up to refresh, and then continues running. So thread 1 continues running here while refresh runs on a background thread. So now we've just introduced what we call a race condition into our app because we have thread 1 modifying our top story collection, and then refresh is still running in the background. And so depending on the timing and your internet connection and how the overhead of thread switching works under the hood, you have another thread that's also modifying your top story collection. And now you have two threads that are going to both hit this. And which one wins? Well, the answer is sometimes thread 1 will hit it first, sometimes thread 2 will hit it first, and thread 1 will hit it second. You never know. That's the problem with a race condition. And that's why they're really hard bugs to fix. You know, when you get that really tough to reproduce user error, because you run the code and it's like, nope, everything worked. But you run the code like 1,000 times and one time it doesn't. That's a race condition that we just accidentally introduced here by using async void because you can't await an async void. So again, that calling thread just continues running. And meanwhile, this is running on a background thread. Now, the other reason async void is dangerous is let's assume refresh throws an exception. So maybe that API call fails, but I'll tell you what, just to really highlight what we're talking about, we'll hard code an exception here. And so you might think to yourself, well, no problem. I can catch exceptions. I'll do a try. I'll do a catch. And then I'll pretend like I'm going to do something here, but I'm never coming back to this. I'm never changing this code. We're just going to ignore it. So, right, we got a try catch block. We're going to catch the exception, right? Well, again, let's walk through it. Let's think about what's happening. So thread 1 calls a constructor. Thread 1 goes into the refresh method. Thread 1 enters the refresh method, hits the await keyword, returns. Thread 1 keeps running. So now thread 1's down here, but this is still running on a background thread. And so if this method, or by the time it gets here, if either of these throw an exception, well, we've already exited our try-catch block. So this is the other reason why async void is dangerous, is because it's nearly impossible to catch an exception from an async void method. So are we going to use async void here? No, because it's dangerous. We got race conditions. We're going to have exceptions. This would be an unhandled exception that would crash our app. So let's put all this stuff back. Let's bring back refresh back up to here. There we go. All right, so we tried async void. That didn't work. Well, something we can do is we can use this extension method that I've created called save, fire, and forget. Now, save, fire, and forget, I'll show you under the hood. And let's see. There we go. So if you look at the code under the hood, and this is all open source, so this is available in a NuGet package, or you're more than welcome to come copy paste it. Under the hood, save, fire, and forget literally just uses async void. But the good news is it has all the guardrails set up for you. So you can call save, fire, and forget and use my implementation of async void and still know that, yes, your task is being awaited. And if you pass in an exception handler, I'll catch that for you, and I'll handle that exception. And whatever code that we end up putting into here will be called. So you can still gracefully handle the exceptions. But the really nice thing with save, fire, and forget is that it's like a big flashing sign that says, thread 1 will continue here while refresh runs on a background thread. So what's nicer about this than using async void, because actually I just remembered I didn't show you if I throw that async void method back in there real quick. Refresh. Close enough. What I want to show you is we kind of get screwed by IntelliSense. Like, this is an async void method, but IntelliSense just goes, nope, private void refresh. And as C# developers, even as senior C# developers, it's a valid assumption to assume that this method will finish running before the next line of code executes. But what we don't know is that it's actually async void, and now all sorts of problems might pop up on our app. Whereas with save, fire, and forget, it's the same idea. We're not waiting for this method to finish running before continuing on in our method. And we're following all the proper guardrails. And we're saying, hey, fellow developers on my team, anybody who's reviewing this code, anybody who's coming along in 5 years that's new to the team, I'm doing this on purpose. So if you ever find yourself in a situation where you don't care when a task completes, like I was saying earlier how I would say, task.run, I don't care when it completes, so I'm not going to wait it. Well, append save, fire, and forget, and we can still get that exception if one's thrown and handle it gracefully. Or if it throws an exception, we still have our exception handler here. So, all right, so first refactor's done. Let's scroll down a little bit, and we see here our next refactor is around this task.delay. So this is kind of a little funky thing. It's a common thing in the mobile app world that when I run this refresh method, I want it to run for at least 2 seconds. In other words, when the user does a pull refresh, I want that little spinning indicator to appear for a couple seconds, because if this API call gets cached and it comes back real quick, it can come back within 100 milliseconds. Well, if that happens, the user might not see it. The user might do a pull refresh, it's 350 milliseconds to blink your eyes. So in a blink of an eye, that little spinning indicator will disappear, and the user will never see it. So a little trick we do, especially in mobile apps, where we can't rely on the internet connection, is we say, all right, I want this method to run for at least 2 seconds. And specifically what I'm doing here is I'm capturing this task, and I'm going to await it later. So this is another trick we can use where you don't have to await a task right away. So again, we want to await every task, but I'm going to kick it off here at the start of the method, and then I'm going to check it later to see, has it been 2 seconds? Wow, did that API call really finish in just 100 milliseconds? Well, we'll still just show the user that activity indicator because that's a better user experience counterintuitively, and you'll get that 5-star review. Now, what we're getting yelled at for is we're not forwarding in our cancellation token parameter. Now, a big, big important thing, another place where I see a lot of junior developers get tripped up, and even senior developers, is every time you create an awaitable method, so in this case an async task method, you have to have a cancellation token as a parameter. Why? Well, you wrote the method, I'm going to call it, I don't know how long your method's going to take to complete. Especially if you're using somebody else's library. Imagine you're installing a NuGet package, it's not open source, you have no idea what this code's doing, and maybe this method might run for 30 seconds. Well, I don't want my user just staring at the screen for 30 seconds and nothing's happening, and then again, I get blamed for it, I get a 1-star review, and they force quit my app and they move on. So the only way to cancel a task is with a cancellation token. And so what I would do is have my token expire after probably 5 or 10 seconds, a reasonable amount of time to stare at a blank screen, and then boop, show the user, hey, check your internet connection, it looks like we weren't able to complete. And so fortunately, the smart folks at Microsoft on the .NET team, they do. They follow the best practice. They allow me to pass in a cancellation token, which means whenever I cancel the token that I pass into here, it'll get propagated forward into task.delay, and it'll cancel this, and just like down below, all my other awaitable methods also propagate that token forward so that those can also be canceled, and it'll all propagate back up thanks to the one token that I passed in. So that's what we want, but let's pretend, right? Let's pretend like I could not pass in a cancellation token, right? Like we downloaded the NuGet package, the developer who made it, they're not async await experts like we are, they didn't give me a cancellation token parameter. Well, a cool trick we can do in .NET is there's an extension method called waitAsync where we can pass in a cancellation token here, and what waitAsync does is it basically bolts on that cancellation token to that task. So the good news is, if you already have a whole bunch of code where you aren't able to pass in cancellation tokens, again, the .NET team's got you covered. So you would just say waitAsync, and then you would bolt on your token here. Now, there's only one small catch with waitAsync is that if this task is already completed, then the token never gets checked. So for example, if we had something like, I mean, this is kind of egregious, but obviously that task is completed, and maybe this token is expired. Well, .NET won't look at the token because it's just going to keep moving on. Remember those optimizations we saw under the hood where it says, hey, is this task already completed? Cool, we don't switch threads. And so if we don't have that thread switch, we don't check the token with waitAsync, that's a small bug that bit me once. So that's one of those like 1%ers that might pop up. So waitAsync, bolt on your cancellation tokens if you're not able to pass one in, or follow the best practices that the engineering team at Microsoft recommends, and make sure all your methods have cancellation token parameters. Great. Moving on. We have our next method here, get top stories. And this looks pretty good. Like we're awaiting it, so we're using async await. That means we're not going to be burning up time on thread 1. What's wrong with this? Well, again, let's think about what's going on, because this refresh method is called when the user does a pull to refresh. So it's a UI event that triggers this method, which means thread 1 will be kicking off the refresh method. Thread 1 comes all the way down to here, hits the await keyword, and returns. Great, so thread 1's still free. We're not overworking thread 1. And meanwhile, get top stories will run in the background thread. And when it's done, remember how .NET will ask that background thread when it's done, it'll say, hey, what was your calling thread? And in this case, it'll say, oh, thread 1 called me. So then what's .NET do? It goes, all right, thread 1, get back in here. So maybe thread 1's busy interacting with the user. Maybe you have a game that's running at 60 frames per second, 120 frames per second. You're really, really working thread 1. It's got to draw in the UI a lot. Well, if we have to wait for thread 1, our code's sitting here idle until thread 1's available. Like this just queues up the work onto thread 1. So we risk our app being a little idle here. So what we can do, or actually, even worse, look at this for each loop down here. This for each loop takes all those stories that we got back from the API and adds them into the collection, but it sorts it first. And so let's imagine this is like 5,000 stories. And then this sorting algorithm, I didn't optimize it. This is probably O of n squared. So we've got 5,000 stories doing an O of n squared sorting algorithm. And if we return to thread 1, well, we just overworked thread 1. Thread 1's going to be busy in this for each loop for a couple seconds. And again, that's bad. So best case scenario, our code sits idle for a couple milliseconds. Worst case scenario, we overwork thread 1. So what do? We can say configure await false. It's an extension method, or I guess just a method in task. And when we call configure await false, what it does, it tells .NET, it tells the runtime, whenever get top stories is completed, don't worry about returning to the calling thread. And in fact, I don't care what thread you return on. You can return on any background thread you want. So now, with configure await false, thread 1 will still call this refresh method. Thread 1 will still make it all the way to the await keyword, return. Now it's hanging out with the user, keeping our app from not being frozen. Get top stories runs on a background thread, and when that background thread is done, we have configure await false. So it'll still notify .NET using iNotifyCompletion and say, hey, .NET, I'm all done. And .NET goes, great, what thread called you? And it goes, configure await false. I don't care. So .NET goes, all right, great. And it just will go to the thread pool and grab whatever thread's available. So our code will never sit here idle, and we never have to worry about it returning to thread 1, the calling thread, and overworking thread 1 here. So highly recommend configure await false. My rule of thumb is anywhere where I don't touch the UI and I don't need to return to thread 1, the calling thread, I configure await false everywhere. So my view models, my services layer, my database layer is just littered with configure await false, because if you're curious, configure await true is just the default. So if you have nothing, having nothing here is the same as configure await true, where it tells you, yes, I want to return to the calling thread. And so we want to override that default and say configure await false. Now, new in, I think it was .NET 8, they also added these configure await options. So these configure await options can be passed in now. And there's 4 options. So they're enum flags, which means they can be chained together. So you can do a bitwise OR operator to pass in multiple options to configure await. And now it gives us a couple extra options. So if we look closely, there is continue on captured context. Well, that's just the same as configure await true. That just says whatever context, whatever thread called me, whatever thread you captured, continue back on that. So configure await true is the same as continue on captured context. It's the worst name I think they could have come up with. I wish I knew why they named it none, but none is the same as configure await false. It means I don't care about returning to the calling thread when I'm done. And then we get these 2 new options. One is suppress throwing. So remember how I was saying we want to await every task because if an exception happens inside that task, we want it to rethrow the exception? That's still true. But .NET now gives us an option that says, hey, even if an exception happens inside of this task, it's cool. I don't need you to rethrow it. Doesn't matter what it is. Suppress all of them, move on. I don't recommend using this. There's very few use cases. I think I've seen it once in production code where it's like, okay, yeah, I guess we could get rid of our try-catch block that's not doing anything and just use suppress throwing, but it makes me uncomfortable. I don't like it because what do we know about code? It gets copy and pasted around. There's going to be another developer that's going to copy paste the suppress throwing somewhere else, and it's going to be future bugs. But it exists. Know about it. I don't recommend it. I try not to use it, and for the most part, don't in my code. And then there's also configure await options.force yielding. And this, if you remember to those compiler-generated code with the optimization where if the task was already completed, we wouldn't switch threads, because .NET's like, hey, I got your back. We're not going to waste time switching threads if a task is completed. Well, if we still want that thread switch to happen, we can call force yielding, and that'll still force a thread switch even if the task is completed. So that one's a fun one. I've used it before where it's like, I need the UI to update, so I still need to free up thread 1, even if this thing is already done, just for a second, so I can maybe draw something on the screen real quick. And so if we wanted to do that, then it'd be configure await options force yielding, and we could also do, like I said, these are flags, so we can chain them together. So I can say configure await options, whoops, let's bring that up here. So I would say configure await options.none to say don't return to the calling thread, chain together with force yielding, which will force that thread switch, and now I know for a fact I'm no longer on thread 1 going forward. So all that to say, even though these are new in .NET 8 and they're a lot of fun to use, I still just use configure await false. So we'll keep this at configure await false, and we'll move on to our next refactor. So finally, we're circling back to that minimum refresh time task. Remember, this is where we said, I'm going to have this task.delay for 2 seconds, but I'm not going to check it yet. I'm just going to kick off this task. As soon as you kick off a task, it starts running. And so this has been running in the background while we've been making the API calls and sorting and updating our collections. And finally, down here, we get to almost complete with the method. But first, I want to say, has it been 2 seconds? Because if it hasn't, don't return just yet. And right now, I'm calling .wait. And .wait's really, really bad. .wait is what we know is a blocking call. .wait, or when you call .wait, it tells .NET to actually hold that calling thread hostage. So if you think about it, when we have a thread hit the await keyword, that thread returns. So we freed up that thread, the calling thread. Meanwhile, the other code's running on a background thread. So we're only using one thread because the await keyword freed up the calling thread. Well, when we call things like .wait and .result, these are blocking calls. They don't free up the calling thread. It says, calling thread, you stay right here, but also at the same time, this task is still running on a background thread. And so what .wait and .result end up doing to us is we're using 2 threads when we should really only be using 1. And worse, if this was thread 1, well, now we're blocking thread 1. Thread 1's not free to go back and interact with the user and update the UI, so also our app's frozen. Duly bad. So with .wait, .result, these are blocking calls. They're not asynchronous. Don't use them. Nowadays with .NET 10, very, very rare where you'd ever need to use .wait or .result. And so the solution here, we would just await it. We'd await it. I still would do a configure await false for a little performance improvement. But sometimes you do still need to use .wait. It's very rare. But if you ever have to use .wait, I have a bit of a recommendation for you, and that's to instead replace it with getAwait or getResult. And actually, this replaces both .result and .wait. Now, getAwait or getResult is still blocking. It's still going to use 2 threads. It's still going to hold that thread hostage. It's not the await keyword. Only the await keyword frees up the calling thread. getAwait or getResult, the reason it's a little bit better than .wait is if you've ever tried to catch an exception thrown by .wait, you'll see it throws what's called a system.aggregate exception. And those are tough to work with because an aggregate exception is an exception that holds exceptions. Like it's got a property in it called inner exceptions, which is a list of exceptions. And inside of that inner list is where your exception would be. So if we had something like an operation canceled exception be thrown, the cool thing with getAwait or getResult, it'll throw our exception. I would be able to catch an operation canceled exception. Whereas with .wait, it would throw a system.aggregate exception, and then I'd have to go one layer deeper to figure out what's the inner exception inside of the aggregate exception. So getAwait or getResult, still bad, still blocking, but if there is a scenario where you have to use .wait or .result, it is just a little bit better, but we don't do that here. We don't want to use that here. So we're going to use the await keyword. And again, another fun fact, yes, you can use await inside of a finally block. OK, coming down to our next refactor, we have this getTopStories method. And the way this is written is how I'm forced to use the Hacker News API. The way the Hacker News API works is I can't just say, hey, give me all the top stories. The way it works is I have to first make an API call to get the top story IDs. And then once I have the top story IDs, I can iterate through those to get each story. And so this method's not really very efficient. I mean, it's using async await, we're using configure await false. All these lessons are good. We're passing cancellation tokens, happy days. But yeah, I mean, what it ends up meaning is the user is just going to be sitting there looking at a blank screen until all, say, 5,000 stories have been pulled back from the API, and then all at one time, they'll appear to the screen. But it's kind of silly because we're going to get that data back. Like, we'll have 4,999 stories before that 5,000th one has finished. What if there was a way we could stream that data to the UI while the user's waiting? Because nothing's worse than staring at a blank screen with just a spinning activity indicator. So in .NET 8, we got this cool thing called async enumerable. Now, I'm just going to copy-paste this code over, save some time here. So we're going to re-implement this as an async enumerable. And I'm going to come back to this because what async enumerable does, there we go. Let's copy-paste that without the red squiggles. Perfect. So what async enumerable does is it unlocks the await for each loop. So you've probably used an await for each loop, and that's because there's a method that implemented async enumerable. So the way await for each works is we'll now say get top stories. Actually, we can keep our configure await false, so let's grab that too. Boom, boom. Fix the order of these parameters, because for some reason I switched them. Not a good reason. And then we can rewrite this code. We'll clear the stories up there, and instead of having this for each loop, we will iterate, or we are iterating in this await for each loop. So we'll jump back down into the async enumerable in just a second. But basically the way it works is similar to an enumerable, if you've ever used one of those, where you can yield return a result. So before the method is done, it can start passing data back up. And so now, as each story is done, so if we're going to retrieve 5,000 stories, when the first API call is done, I can pass that into my top story collection, and all of a sudden, the user starts seeing data streaming in instead of just sitting there looking at a blank app. So we get a much, much better user experience. And even though it's still going to take the same amount of time to get all of the data, the user's going to start seeing data ahead of time, and it's going to feel like it's a lot faster because we're streaming this in thanks to async enumerable. Now, jumping back down here, how does all this work, right? Well, what we're doing is we still have to get all those top story IDs, so I still have to make this API call to get the top story IDs. But then what I'm doing is I'm building a list of tasks. So we have a list of tasks of story model here. And this select statement, this is just a kind of a cheeky way to say, for every top story, call get story and pass in that ID here. And what we get is just a list of tasks. So we've just fired off 5,000 tasks. They're all running in the background. I mean, in reality, we probably don't have 5,000 threads, so .NET's going to manage all that for us. Don't worry about it. So we fired off all these tasks, and then in .NET 10, we got a really cool extension method, which is right here, this toAsync enumerable, where it basically says, for this list of tasks, as each task finishes, and here, let's do it like this. This is a task of story, and then we'll say var story equals await that top story task that's completed. And then we'll just yield return that story. There you go. Break out the code a little bit more. Make it a little bit more verbose. There we go. So right, we've fired off all these tasks that are in a list, and now we can say toAsync enumerable, and we have another for each, await for each loop down here that as soon as each task is completed, then .NET automatically is going to enter into this await for each loop and yield return the story. And as soon as we hit yield return, our code actually comes back up here and enters in here and starts adding it to the collection. So Much, much better user experience because we can stream that data to them. Now, if you're not yet on .NET 10, you won't have access to this toAsync enumerable extension method. So in .NET 9, task when each was added. There we go. So if you're still on .NET 9, haven't gotten to .NET 10 yet, you can use task.whenEach. It's literally the same thing. The extension method is what I prefer because I like how it reads. Like, when you see task.whenEach, you're like, when each what? Well, it just returns an async enumerable. So .NET 9, task.whenEach, .NET 10, boop, toAsync enumerable. They didn't give us the ability to pass in a cancellation token here on toAsync enumerable, but no worries. There's another method called, another extension method that exists called with cancellation. So if you're using an async enumerable, you call with cancellation to pass in your token. You can still configure await false it like we know and love. And now we have a much more performant app. Now, the other thing I want to point out here is this enumerator cancellation attribute. So again, this is an awaitable method, so I want to have a cancellation token parameter because I'm a good C# developer. And so if you forget about this, don't worry too much. At least JetBrains reminds me, hey, you forgot that. I'll put it back in there for you. This is really cool because what this does, this tells .NET to take my token that I pass in and inject it into moveNext. So remember that moveNext, that iterator that's on any enumerator. Now every time this await for each loop loops, .NET automatically checks my token for me. So I don't have to worry about checking to see if the token's canceled or throwing if it's completed. So you get this nice little cheat code, this nice little performance optimization with enumerator cancellation. So async enumeral is great. Highly recommend it if you want to stream data faster instead of having to wait for everything to complete in a task and just dumping it all at once. Async enumerable will give you that data as it comes. OK, we're running short. Let's super fast. We have a method down here, getStory. getStory calls this API service. And if we look at it, this returns a task of type story model, but so does our method. And so the only place we're using the await keyword in this method is in the return statement. And that means we can actually remove the await keyword, remove the async keyword, and just return the task. And what that does, it saves us a thread switch. Because if, let's say, thread 5 calls this method, well, thread 5 would come in here, hit the await keyword, return back to the thread pool. getStory will run on a background thread. When that thread's done, then thread 5 comes back in here just to return the result. So instead of doing a couple extra thread switches here, whoops, we can just return the task, and everything still works as expected without that extra thread switch. Now here in this next example, again, the only place where we use the await keyword is in the return statement. And if I look at this method signature, it's the same as what I'm returning, a task of I-read-only list of longs. Cool. So right, this is what we just talked about. I delete this, I delete this. Happy days, ignore these squiggles here, because that's not the point of this. But this is actually a trick question, because here we're inside of a try-catch block. And so if we return the task, we exit the method. So we exit the try-catch block right away. So if you think about it, thread 5, let's say thread 5 calls this method, thread 5 hits the return statement, and thread 5 just goes, OK, and it returns the task. We've exited the try-catch block. If this throws an exception, we're never going to catch it here. So be careful with returning tasks, because if you have a try-catch block, you still want to await it, because we want this task to run to completion, so we can use the await keyword to rethrow that exception while we're still here inside the try-catch block. Now, the optimization that we do want is actually up here, because I've got a little optimization here where I'm going to get the top story IDs, but if it's only been an hour since the last time I fetched them, I don't need to do it again. I already got them. The top stories don't update that much. So the first time this method runs, we're going to come down here, and we're going to use the await keyword to call that API. But the second time this method runs, we're not going to use the await keyword. And the third time this method runs, we're not going to use the await keyword. The fourth time this method runs, we're not going to use the await keyword. In other words, this is the hop path of our method. And the hop path for our method does not use the await keyword. And if you find yourself in that situation, switch that task to a value task. The value task is similar to task, but it's a value type, meaning it's initialized on the stack, whereas a task is an object, it's a reference, meaning it's initialized on the heap. And if you remember from your data structure classes, to add something to the stack, O of 1. To add something to the heap, O n log n. So you get a little initialization performance benefit by using value task when you don't necessarily need the async await overhead of a task. Now, they're not exactly the same. Like, you can't reuse value tasks. You shouldn't pass around value tasks. But if you just change your return type and treat it like you would normally, just await it, no problems, happy days, nice little performance improvement. OK, we are out of time, but this is just a review, so we'll speed through it. Never use .wait, never use .result. If you need to, you can use getAwaiter to get result, but highly, highly recommend always using the await keyword. Fire and forget tasks. If you don't want to wait for a task to finish, you can use safe fire and forget. It'll still follow all the best practices under the hood. If the exception gets thrown, you can still catch it, you can still handle it, and it alerts all the users, all the other developers that, hey, we know this is going to run in the background, and we're going to continue running below it while not awaiting it. And you can find that in the async await best practices NuGet package. Avoid return await. So if you have a method where you only await in the return statement, you can remove that and just return the task, save yourself a thread switch. Just be careful and try catch blocks and disposing using blocks. You still want to keep async await, because otherwise you're going to return out of that disposing block, and you're going to .NET's going to dispose that object on you. I've hit those bugs. Don't make the same mistakes I did. Configure await false. So only if you need to return to the calling thread, when you don't need to return to the calling thread, use configure await false. And there's a subtle additive here. I'll give you some more information in just a second. Configuration context, or synchronization context. All the UI applications in .NET, with the exception of ASP.NET Core, have a synchronization context. The synchronization context is required for switching back to the calling thread. So when ASP.NET Core was created, they made the design decision to not add a configuration context for a little bit of performance improvement. So a little bit different behavior there. And I'll help you out in a second on how you can learn more about that. Configure await options. So there's continue on captured context, force yielding, suppress throwing, and none. They're flags, they're enums. You can chain them together. I don't recommend using suppress throwing, but if you need to force a yield, use that. Utilize value task. If a method's hot path doesn't use the await keyword, we can use value task for a little bit of a performance bump. Async enumerable for streaming data allows us to update the UI, better user experience. Just don't forget that enumerator cancellation attribute on your cancellation token parameter. Wait async exists, so if you ever have to call a method that doesn't give us a cancellation token parameter, you can bolt yours on using .wait async. And we didn't touch on this yet, but async disposable. So just like we can use using statements to dispose of unmanaged resources when we're done, there's also async disposable. It still allows us to call configure await false, but the syntax is a little weird because the await keyword is up here. But in reality, all the code below the await keyword inside these curly brackets is going to run, and we won't await or do any thread switching until we exit the curly brackets. So for await usings, use them if there's one available to you. That means the developer knows that, hey, this is going to be a long time. Use async disposable instead. But just remember that await doesn't happen until you exit the using block. OK, so I mentioned synchronization context. There's so many more things about async await, about execution context, async local, thread static. There's so much more that we just can't cover, and I'm already over time just with what we did. So I wanted to highlight to you, I've created a couple tasks on Dome Train. They're actually here. They've got a booth downstairs if you want to go hang out with the guys. But we have asynchronous programming course that I've created, so you can spend another 4 hours with me there, going even deeper into what we covered today. And then if you want to keep going, I've just published this parallel programming course, which is adding onto that and another 3.5 hours of hanging out with me, doing nothing but async await stuff. That one focused on parallel programming. And we showed .NET MAUI. It has nothing to do with the session today, but if you're interested and you like what you saw with the .NET MAUI app, I also have a couple .NET MAUI courses, so you can spend another, 10.5 hours with me on Dome Train once you're done with all the async await courses. OK, if you haven't already had the chance, now is the time to take out your phone, grab a picture of this QR code, because again, this is where you can find everything we covered today. So if you're interested in the slides, if you want the recording of the session, all of that's available on the website. I've linked there the Dome Train courses for us, as well as all the code, the async await best practices NuGet package. Everything we covered today is available here on my website at codetraveler.io/async await best practices. Thank you.